What if everything we think we know about the beginning of the universe is just the tip of an unimaginably strange iceberg? Picture this: not a fiery explosion, not a singular point of infinite density, but a reality where the cosmos itself existed in a quantum superposition, a state where multiple possibilities flickered into being simultaneously. This isn't science fiction, it's one of the most mind-bending frontiers of modern physics, and it challenges our very understanding of existence. Today, we're diving into 30 astonishing theories about the universe's first quantum state, ideas so radical they'll make you question the fabric of reality itself. Imagine the birth of everything not as a single event, but as a cosmic dice roll where every possible outcome played out at once. Quantum mechanics tells us particles can exist in multiple states until observed, but what if that principle stretched across the entire early universe? What if the seeds of galaxies, stars, and even time itself were born from a primordial quantum fog, where probabilities danced and reality hadn't yet chosen its path? The implications are staggering. It means our universe might just be one thread in a vast, shimmering tapestry of parallel beginnings, each with its own laws, its own destiny. This is where the line between physics and philosophy blurs. If the universe began in a quantum superposition, what or who collapsed it into the reality we know? Was it sheer chance or something deeper? And if other versions of that first moment still linger unresolved, could they hold the key to mysteries like dark energy or the arrow of time? Over the next 30 theories, we'll explore ideas that range from the elegantly simple to the wildly speculative, from quantum fluctuations in the void to holographic origins and cosmic entanglement. Strap in, this isn't just a journey through space and time. It's a voyage into the very heart of possibility, where the rules we take for granted might just be the first layer of a far stranger truth. The very first moments of our universe might have been far stranger than a simple Big Bang. What if it was more like a cosmic version of Schrödinger's famous cat, simultaneously alive and dead until someone peeked inside the box? This is the Schrödinger's cosmos hypothesis, a mind-bending theory suggesting the entire universe existed in a quantum superposition, a hazy blend of all possible initial states before somehow snapping into the reality we recognize today. Think of it like flipping a coin, only instead of heads or tails, the universe was both at once and every other conceivable outcome in between. In quantum mechanics, particles can linger in multiple states until an observation forces them to choose, a phenomenon we see in labs with electrons and photons. But scaling this up to the birth of everything, that's where things get wild. If the early universe was in a superposition, then time, space, even the laws of physics themselves might have been undecided, flickering between possibilities like a cosmic light bulb that hadn't settled on being on or off. So what caused this quantum fog to collapse? Some physicists point to quantum decoherence, the idea that interactions with the environment eventually force a system to pick a state. But in the primordial universe, what counted as the environment? Was it the first particles forming or something else entirely? Here's where the observer problem kicks in. In quantum theory, measurement plays a mysterious role. Does reality require a conscious observer to solidify it? If so, who or what was watching the birth of the cosmos? Maybe the answer lies in the universe observing itself, a self-resolving paradox where the act of existence broke the superposition. Or perhaps there was no collapse at all, just branching realities, each tracing its own path from that quantum haze. Picture an infinite hall of mirrors reflecting every possible version of creation, with our universe just one reflection among countless others. Visualizing this isn't easy, but imagine a cosmic-scale cat-in-a-box experiment. Instead of a feline in a container, it's the entire universe trapped in a state of quantum ambiguity until snap reality crystallizes. whether by chance, necessity, or some undiscovered law. That moment of resolution shaped everything we know. And if other branches of that initial superposition still exist out there, it means our universe might just be one answer to a question that once had infinite replies. What if our universe wasn't the only one to emerge from that primordial quantum soup? What if it was just the first domino to fall in an endless chain of cosmic possibilities? That's the heart of the multiverse bootstrapping theory, a radical idea suggesting the universe's initial superposition didn't collapse into a single reality, but instead fractured into countless parallel worlds, each with its own unique set of physical laws. Think of it like a cosmic tree growing infinite branches, where every quantum decision, every flicker of uncertainty in those first moments spawned a new universe. This hinges on a process called quantum branching, where a system in superposition doesn't settle on one outcome but splits into multiple timelines, each carrying a different version of events. In the lab, we see this on a tiny scale, particles taking all possible paths simultaneously. But stretch this to the birth of everything, and suddenly, you're not just talking about electrons doing quantum acrobatics. You're talking about entire universes budding off from one another, each with its own version of gravity, light speed, even the number of dimensions. Some might have stars that burn forever, others could collapse instantly into black holes. The constants we think of as fixed, the strength of forces, the mass of particles, might just be local bylaws in one cosmic neighborhood among endless others. Now here's where physicists hit a snag. If these other universes are truly separate, how could we ever test their existence? Critics argue this veers into philosophy, not science after all. If something can't be observed or measured, does it belong in a lab or a thought experiment? But supporters counter with eerie clues, like mysterious voids in our cosmos where the laws of physics seem subtly off, or the fine-tuning problem. Why do our constants fit so perfectly for life unless there were infinite attempts? It's like finding a single perfectly sanded grain of sand on a beach and realizing the ocean must have eroded countless others to produce it. Picture this as a cosmic version of a choose-your-own-adventure book, where every quantum decision in the early universe ripped the page in two, creating divergent storylines. Our reality might just be one sentence in an infinite library of possibilities, each bookbinding holding a universe where gravity is stronger, time runs backward, or life never sparked at all. The controversy isn't just about whether this is true, it's about whether science can ever truly know. But if the math holds, the multiverse isn't just a wild guess. It might be the inevitable consequence of a universe born in quantum uncertainty, forever branching into the unknown. What if the universe's first quantum superposition wasn't just a blur of possibilities but a cosmic blueprint, a two-dimensional code that somehow rendered our three-dimensional reality into being? This is the holographic genesis model, a theory that marries quantum superposition with one of the most radical ideas in modern physics, that our universe might be a projection, a hologram etched onto a distant, flat surface. Think of it like a movie screen where every star, every galaxy, even the fabric of space-time itself, is just a pixelated image emerging from something far simpler, a quantum canvas operating in fewer dimensions. The roots of this idea stretch back to black holes, those cosmic paradoxes where gravity twists reality into knots. Physicists studying them made a bizarre discovery. The information swallowed by a black hole isn't lost forever. Instead, it gets smeared across its event horizon, the point of no return, like a message written in vanishing ink. This suggests that a three-dimensional object, a star, a planet, even you, could theoretically be encoded on a two-dimensional surface. Now take that logic and stretch it back to the universe's birth. If a black hole's contents can be holographically stored, why not the entire cosmos? Here's where superposition crashes the party. In those first fleeting moments before reality chose its form, the universe might have existed as a quantum haze of overlapping states, not just in our familiar dimensions, but on a primordial 2D boundary. Imagine a flickering, pixelated grid where every possible configuration of the universe, every potential law of physics, every arrangement of particles existed simultaneously, like a cosmic DVD waiting to play. The act of collapsing that superposition could have been what rendered our 3D world into existence, translating quantum uncertainty into the solid universe we recognize. But how do we even begin to test such a wild idea? Some clues come from the fabric of space-time itself. At the tiniest scales, physicists suspect space isn't smooth but grainy, like a digital image zoomed in too far. If the universe is truly holographic, there should be a fundamental limit to how much information any region of space can hold, a cosmic resolution limit. Experiments with quantum gravity and particle accelerators are hunting for these pixels of reality, subtle glitches that might betray our universe's true, flattened origins. Picture this as the ultimate cosmic magic trick, a universe that appears vast and three-dimensional, but is really a shadow cast by quantum interactions on a distant, flat surface. It's a dizzying thought that everything we see, from the spiral arms of galaxies to the glow of your screen right now, might just be the universe's way of resolving its own quantum uncertainty, unfolding from a 2D code into the rich, layered reality we experience. And if that's true, it means the answers to the universe's deepest mysteries might not be hidden in the stars, but in the quantum fine print of existence itself. In the eerie quiet of what we call empty space, there's a seething, invisible dance of particles popping in and out of existence, a quantum foam so restless, it might have been the spark that ignited reality itself. This is the quantum fluctuation origin theory, a mind-bending proposal that our universe didn't emerge from a singularity, but from a wrinkle in the fabric of nothingness. Imagine a vast, dark ocean where tiny waves suddenly surge into tsunamis, except here, the waves are pockets of energy flickering in the void, and one of them swelled into everything we know. At the heart of this idea lies zero-point energy, the lowest possible energy a quantum system can have. Even in perfect vacuum, space isn't truly empty. Instead, it's a frothing sea of virtual particles, electron and anti-electron pairs, quarks and antiquarks blinking into existence for fleeting moments before annihilating each other. Most of these fluctuations cancel out instantly, but what if one didn't? What if, in those pre-Big Bang depths, a quantum hiccup stretched too far, injecting enough energy to tip the scales from void to cosmos? It's like a single bubble in a boiling pot growing so large it transforms the entire pot into steam. Critics pounce on the obvious question: how can something come from nothing? Proponents argue it's not nothing at all. Quantum foam isn't emptiness, it's a simmering grid of potential where the rules of cause and effect blur. In this view, the universe isn't a magician's rabbit pulled from a hat. It's more like a dormant seed cracking open under the right conditions. The energy for creation might have been borrowed, with gravitational fields acting as cosmic creditors, balancing the books over billions of years. Visualizing this is like trying to sketch static on an old TV screen, an unpredictable crackle of possibilities. Some models depict the quantum foam as a labyrinth of tunnels and bubbles where universes sprout like buds on a fractal vine. If true, our reality might be one bubble in an endless froth of cosmic foam, each with its own physics, its own destiny. Yet the debate rages: does this truly solve the something from nothing paradox, or just kick it down the road? After all, where did the quantum foam come from? The equations hint at a deeper layer, a self-sustaining cycle where universes emerge, collapse, and rebirth from the same quantum substrate. It's a dizzying thought that existence might not need a starting gun, just the endless churn of a quantum sea, forever birthing new worlds from its depths. Could the act of observation, of simply looking at the universe, have been the force that snapped reality into existence? This is the spine-tingling premise of the conscious observer collapse theory, which takes one of quantum mechanics' most famous paradoxes and scales it up to cosmic proportions. At its core is the von Neumann-Wigner interpretation, a controversial idea suggesting consciousness itself might be the glue that holds reality together. Imagine the early universe as a trembling quantum mirage flickering between infinite possibilities until the first flicker of awareness somewhere somehow forced it to choose. The math behind this isn't just speculative. In quantum experiments, particles exist in superposition until measured, as if they're waiting for an observer to decide their state. But who or what counts as an observer? Traditional physics says it's any interaction with the environment, but visionaries like Eugene Wigner argued it's consciousness that collapses the wave function, stitching probability into solid fact. Extend this to the universe's birth, and you're left with a staggering implication. Reality might have remained a hazy quantum dream until the first spark of perception, like a tree falling in a forest with no one to hear it except here. The tree is all of existence. Materialist physicists fire back with a simple rebuttal. Consciousness is an emergent property of brains which are made of particles obeying quantum rules. How could something dependent on physics turn around and define physics? It's a chicken and egg problem wrapped in a paradox, yet supporters counter with eerie parallels in cosmology. The fine-tuning of our universe, its impossibly precise constants that allow for life, almost seems tailored for observers to emerge. Coincidence or something deeper, like a cosmic feedback loop where observation and creation are entwined. Picture this as the ultimate act of participatory creation. Not a distant deity sculpting the cosmos, but reality crystallizing under its own gaze, like a painter who only sees their canvas when they first open their eyes. If true, it means our own awareness might be part of an ancient chain reaction, that every time we look at the stars, we're echoing the primordial act that made them. The debate rages on, straddling the line between physics and metaphysics. But whether it's profound truth or poetic speculation, one thing's certain: it redefines what it means to be a witness to the universe's story. What if the first quantum state of the universe didn't just blur space but shattered time itself? The time-symmetric superposition theory proposes something even stranger than parallel universes, a beginning where past and future were entangled, a cosmic knot where cause and effect flowed both ways. Picture time not as an arrow but as a Möbius strip twisting back on itself until before and after lost all meaning. In this view, the Big Bang wasn't a starting gun. It was a collision between two eternities, a handshake between creation and destiny. This isn't just philosophy. Quantum experiments already hint at time's flexibility. Take retrocausality, the mind-bending phenomenon where particles seem to respond to events before they happen. In labs, scientists have seen photons adjust their behavior based on measurements taken later, as if the future were whispering to the past. Meanwhile, Richard Feynman's path integral formulation paints a universe where particles don't just move forward in time. They explore every possible path simultaneously, zigzagging through history like cosmic time travelers, weighting their routes by probability. Now scale this up to the universe's birth. What if those primordial quantum fluctuations weren't just random noise, but echoes of a reality where time was a two-way street? The implications rewrite the origin story we know. If the early universe existed in a time-symmetric superposition, then the conditions that birthed galaxies might have been shaped by future events like a cosmic Ouroboros where the tail feeds the head. Dark energy's mysterious push, the universe's accelerating expansion, even the eerie fine-tuning of physical constants could all be footprints of this temporal tango. Some models suggest black holes might be knots in spacetime where this symmetry snaps, creating one-way doors in the fabric of cause and effect. Visualizing this demands a total rethink of time's arrow. Imagine a particle's journey not as a line but as a branching tree with roots in the future and branches in the past. The universe's first quantum state might have been a kaleidoscope of overlapping timelines, each influencing the other until somehow the flow we recognize as now emerged. Experiments with quantum entangled particles already show actions on one instantly affecting its partner, regardless of distance. If time is just another dimension, why wouldn't it obey the same rules? Yet skeptics ask, if time symmetry was real, why don't we remember tomorrow? The answer might lie in decoherence, the same process that collapses quantum superpositions in space. Just as observing a particle chooses its position, the act of living forward might edit the past, cementing one timeline while others fade into unreality. It's a dizzying thought that the universe's first moment wasn't a beginning at all, but a midpoint in an infinite loop where every now is just a ripple between two eternities. And if that's true, then somewhere in the quantum static of deep space, the future might still be writing the past. What if our universe didn't emerge alone? What if it was just one thread in a vast, invisible web of cosmic connections, all humming in perfect quantum harmony? This is the entangled baby universe's theory, a spine-tingling idea that the universe's first quantum state wasn't a solo act, but a chorus of entangled realities, each influencing the others instantaneously, no matter how far apart they stretched. Picture a spiderweb glistening with dew where every strand trembles when you touch just one. Now imagine each droplet is a universe and the silk threads are quantum links binding them together even as they drift apart. Quantum entanglement is one of the most baffling phenomena in physics. When particles become entangled, they share a single quantum state, so that measuring one instantly defines the other, no matter the distance. Einstein famously called it spooky action at a distance, but in labs it's undeniable. Now stretch this to the cosmic scale. If the early universe was a quantum superposition, why couldn't it have been entangled with others? In this view, the Big Bang wasn't a solitary explosion. It was a synchronized snap, one ripple in a vast network of birthing universes. Each one collapsed into its own reality, but the ghostly threads of entanglement might still linger, weaving through dimensions we can't see. The implications are staggering. If universes are entangled, then the laws of physics in ours, the speed of light, the strength of gravity, might not be arbitrary. They could be locked in a cosmic balance with countless other realities, like tuning forks resonating across the multiverse. Some physicists speculate this could explain the eerie fine-tuning of our universe. The constants aren't random, but harmonized with an unseen symphony of other worlds. Visualizing this is like trying to map a city using only echoes. We might never see these sibling universes directly, but if entanglement holds, their fingerprints could be hidden in the cosmic microwave background, the faint afterglow of the Big Bang, or in the way black holes seem to know things they shouldn't. Experiments with quantum gravity could one day reveal subtle tremors in spacetime, hints that our universe is still whispering to others across the void. Critics argue this veers into untestable speculation, but supporters counter with a tantalizing clue. Quantum entanglement defies classical intuition too, yet it's real. If particles can stay linked across galaxies, why not universes? Picture a cosmic version of Schrödinger's box, where opening it doesn't just reveal a live or dead cat, it spawns infinite boxes, each holding a different outcome, all still mysteriously in sync. Our reality might just be one measurement in a web of possibilities, forever tied to the others by threads we're only beginning to glimpse. What if the entire universe we perceive, the stars, the planets, everything isn't real at all, but just a fleeting hallucination of a single, lonely brain floating in the void? This is the Boltzmann brain paradox, a nightmare scenario born from the marriage of quantum superposition and thermodynamics that keeps physicists awake at night. Picture a universe where chaos reigns supreme, where random fluctuations in the cosmic soup occasionally spit out fully formed, self-aware minds' brains that blink into existence, complete with false memories of a past that never was before dissolving back into the noise. Now imagine you are one of those brains, and everything you've ever known is just a phantom projection of quantum accident. The roots of this horror story stretch back to Ludwig Boltzmann, the physicist who first grappled with entropy, the universe's slow slide into disorder. He realized that given enough time, even the most improbable events become inevitable. In an infinite, chaotic cosmos, atoms could randomly assemble into a functioning brain, complete with the illusion of a coherent world. Quantum superposition cranks this up to 11. If the early universe was a haze of probabilities, why couldn't one of those possibilities be a fully formed observer, complete with a fabricated reality? It's Schrödinger's cat with a cosmic twist, not just a box with a live or dead feline, but a box containing you, unsure if you're part of a vast universe or just a statistical blip. Here's why this terrifies scientists. It undercuts everything we trust about reality. If Boltzmann brains are possible, they're statistically more likely than the ordered universe we think we inhabit. After all, conjuring a single brain from randomness requires far less energy than crafting an entire cosmos. The odds suggest we should all be Boltzmann brains, adrift in the dark, dreaming of galaxies. Yet here we are, seemingly anchored in a stable, shared reality. So why isn't the sky full of disembodied minds screaming into the abyss? Some argue that the very fact we're asking the question disproves the idea. Our consistent observations of a lawful universe hint at something deeper. Others propose a cosmic censorship. Maybe the universe's quantum rules prevent such aberrations from lasting long enough to matter. Visualizing this feels like staring into an existential funhouse mirror. Imagine drifting through infinite blackness, your thoughts the only proof you exist, while around you, other phantom brains flicker like dying light bulbs, each convinced their hallucination is real. It's a cosmic horror story written by the laws of physics themselves, but there's a twist. If the early universe truly was a quantum superposition, then the Boltzmann brain paradox might be a clue, not a curse. Perhaps the act of observation, of being an observer, is what collapses the probability wave into a stable reality, weeding out the chaotic flukes. Or maybe the answer lies in the holographic principle, where information is so tightly bound that illusions can't sustain themselves. Either way, the paradox forces us to confront the fragility of existence. Are we the product of 14 billion years of cosmic evolution, or just a hiccup in the quantum static? The unsettling truth is that physics can't yet rule out either possibility. What it can do is push us closer to understanding why reality feels so real, and whether that feeling is the universe's greatest joke or its deepest mystery. What if the universe's first quantum state wasn't a dice roll of probabilities, but a cosmic river flowing along an invisible current? Enter the pilot wave quantum beginning, a radical twist on quantum mechanics where the universe's birth wasn't ruled by chance, but steered by hidden forces guiding every particle into place. This theory resurrects an old challenger to mainstream quantum thought, Bohmian mechanics, the idea that particles aren't ghostly clouds of probability, but tiny specks riding a deterministic wave like leaves caught in a preordained tide. Mainstream quantum theory tells us particles have no definite properties until measured. They exist as probability waves smeared across space. But Bohmian mechanics flips the script. Particles always have precise positions, secretly choreographed by a pilot wave that orchestrates their paths behind the scenes. Scale this up to the Big Bang, and suddenly the universe's quantum haze wasn't a free-for-all of possibilities. It was a symphony with a hidden conductor, a cosmic blueprint guiding the collapse into reality. Visualizing this is easier than you'd think. Just watch oil droplets bouncing on a vibrating fluid. In lab experiments, these droplets mimic quantum behavior, eerily tracing paths that mirror atomic particles when guided by waves in the liquid. It's a macroscale hint that what we call quantum randomness might be the surface ripple of something deeper, a hidden layer of physics we've yet to map. But why does this split physicists into warring camps? Because it challenges quantum orthodoxy at its core. Standard theory insists reality is fundamentally probabilistic, that God does play dice with the universe. Bohm's pilot wave, it's a throwback to determinism where every event traces back to hidden variables. Critics pounce on its lack of experimental distinction from mainstream quantum mechanics. If both theories predict the same outcomes, is the pilot wave just metaphysical baggage? Supporters counter that it resolves quantum paradoxes like wave-function collapse without invoking multiple worlds or conscious observers. Picture the early universe as a stormy sea, with every particle's path etched by the pilot wave's unseen hand. The equations suggest this wave could have guided the universe's first quantum state into the reality we see, like an artist's brushstrokes resolving a blurry canvas into sharp detail. Whether this hidden hand still shapes the cosmos today or faded into the background after creation remains one of physics' most electrifying unsolved riddles. And if the pilot wave is real, it means the universe might not be a casino after all, but a grand machine with gears we're only beginning to glimpse. Imagine the early universe as a quantum gladiator arena where trillions of wave functions clashed in a battle for survival, not with swords but with mathematics. This is the heart of quantum Darwinism, a theory suggesting the cosmos didn't just stumble into stability. It earned it through a ruthless process of natural selection at the quantum level. Picture trillions of overlapping realities, each jostling for dominance until only the most resilient, the ones best suited to endure, collapsed into the universe we recognize today. At its core, this idea flips traditional quantum mechanics on its head. Instead of a single observer magically collapsing probabilities, the environment itself acts as a sieve, amplifying certain quantum states while suppressing others. Think of it like a cosmic game of telephone, where only the clearest, most robust messages get passed along through the noise. In the primordial chaos, some wave functions would have been fragile, crumbling under the slightest interaction. Others, those describing stable configurations of matter, energy, or even space-time itself, would have been reinforced by their surroundings, their patterns copied and echoed until they became the default setting for reality. This isn't just poetic analogy. In labs, we already see hints of this process. When quantum systems interact with their environment, whether it's a stray photon or a passing atom, certain states leave more footprints than others. These preferred states are the ones we eventually measure, not because they're inherently special, but because they're the ones durable enough to survive the gauntlet of decoherence. Now, stretch this to the universe's infancy. The quantum fog of creation wasn't just a static cloud. It was a dynamic ecosystem where physical laws emerged not by decree but by fitness. Those early configurations that could resist unraveling, that could consistently replicate their structure despite the chaos, were the ones that stuck around long enough to build galaxies, stars, and us. Critics argue this borrows too liberally from biology, grafting Darwin's framework onto physics where it might not belong, but supporters point to eerie parallels in cosmology. Why do we live in a universe where matter clumps so perfectly into galaxies, or where the vacuum energy is so improbably fine-tuned? Quantum Darwinism offers a grimly elegant answer, because universes where those conditions didn't hold were evolutionary dead ends, collapsing back into noise before they could even blink into existence. Visualizing this demands a shift in perspective. The early universe wasn't a blank slate. It was a quantum jungle where the fittest states weren't the strongest, but the ones best at turning randomness into rhythm. The constants we take for granted, the speed of light, the strength of gravity, might be cosmic fossils, relics of a billion failed experiments where less robust laws flickered out unseen. It's a humbling thought that the order we cherish isn't the universe's first draft, but the winning entry in a contest we'll never see the full entries for. And if that's true, then every atom in your body, every photon streaking from a distant star, is here because its quantum ancestors outcompeted the alternatives in a battle without witnesses. What if the universe's first quantum state wasn't a singular event, but a cosmic echo reverberating from the edge of a higher dimensional realm? Enter the AD/CFT quantum nursery, a theory that stitches together superposition and string theory's most enigmatic playground untied to Sitter space. Picture this: our universe isn't the main act, but a holographic shadow cast by quantum fireworks happening on a distant, multidimensional boundary. It's as if reality is a mural painted by particles we can't see, dancing in dimensions we can't touch. At the heart of this idea lies a radical twist on string theory's framework. Untied to Sitter space, or AD-S for short, is a bizarre geometric construct where space-time curves inward like a saddle, stretching infinitely yet bounded in ways that defy intuition. In this model, our four-dimensional universe could be just one slice of a higher dimensional bulk, like a soap bubble floating in a vat of unseen forces. But here's where superposition crashes the party. The quantum state of the early universe might not have originated within our dimensions at all. Instead, it could have been a projection, a hologram, encoded on the boundary of this AD-S space, a cosmic scribble of quantum information that somehow rendered our 3D reality into being. Think of it like a cosmic version of a vinyl record. The grooves on the disc, the boundary, hold all the information needed to recreate the music, but the actual sound waves, our universe, only emerge when the needle touches down. In the AD-S/CFT correspondence, the grooves are quantum fields vibrating on the edge of untied to Sitter space, and the music is everything we perceive as real. The early universe's superposition, then, wasn't just a blur of possibilities, it was a higher dimensional symphony, with every potential outcome humming in unison until the needle of decoherence dropped, collapsing the quantum harmonies into the single track we call reality. Lab experiments can't yet probe these extra dimensions, but the math hints at eerie clues. Black holes, those cosmic paradoxes, behave eerily like holograms. Their interiors might be empty, with all the information smeared across their surfaces. If true, why couldn't the entire universe follow the same rules? Some physicists speculate that the Big Bang's quantum fog was just the moment our 3D projection flickered to life, like a light bulb switching on in a room we didn't know existed. But how do we test something so abstract? The answer might lie in the fabric of spacetime itself. If our universe is truly a hologram, there should be subtle glitches in how information scales, a cosmic pixelation effect hidden in the vibrations of particles or the way gravity bends light. Experiments with quantum entanglement and high-energy particle collisions are hunting for these fingerprints, searching for proof that we're not just living in the universe, but on it, a quantum tattoo etched onto the skin of something infinitely stranger. Visualizing this demands a leap of imagination. Picture a flock of birds soaring over a lake. Their reflections ripple on the water's surface, but the real action is happening in the air above. Now imagine the reflections start building cities, forging stars, unaware they're just shadows of a deeper dance. That's the AD-S/CFT nursery in a nutshell, a universe convinced it's the main event when it might just be the encore. And if that's true, then somewhere, in dimensions beyond our grasp, the quantum seeds of creation are still whispering, waiting to be read. What if the fabric of space-time wasn't smooth and continuous, but more like a cosmic patchwork quilt, a tapestry woven from tiny, indivisible stitches of reality? This is the essence of loop quantum gravity's take on the universe's first quantum state, where the primordial soup wasn't just a blur of probabilities, but a buzzing network of spin networks, trillions upon trillions of interwoven loops defining the very pixels of existence. Picture a vast digital canvas where each pixel isn't a static dot, but a vibrating knot of space-time itself, humming with potential until the right combination snapped into place, stitching together the cosmos as we know it. Unlike traditional quantum theories that treat space as a passive stage, loop quantum gravity suggests space-time is an active participant, a granular, dynamic entity built from these spin networks. Imagine a child's toy construction set where each plastic rod and connector represents a quantum of space. In the early universe, these rods wouldn't have been fixed. They'd exist in a superposition of every possible configuration, a shimmering kaleidoscope of potential geometries. The act of the universe choosing its shape wasn't a gentle collapse, it was more like a cosmic game of musical chairs where the music stopped and all those quantum loops suddenly locked into the pattern we now call reality. Here's where it gets wild. These spin networks don't just describe space, they are space. A single loop might represent a volume smaller than a quadrillionth of a proton, but woven together, they form the scaffold of everything: galaxies, planets, even the vacuum between stars. In the universe's first moments, these networks wouldn't have been orderly. They'd have been a churning sea of possibilities, with loops entangling, overlapping, and dissolving like ink dropped in water. Only when certain configurations proved stable, when the knots in the network could hold under the universe's expanding weight, did structures like time and dimensionality emerge. Visualizing this is like trying to watch a storm through a kaleidoscope. Each shard of glass is a quantum of space, and with every twist, the entire image changes. Some models depict the early universe as a foam of these loops, where bubbles of stable geometry occasionally surfaced, only to pop back into chaos. Our universe might be one of those bubbles that didn't pop, a rare, self-reinforcing pattern that grew large enough to outlast the quantum turbulence around it. The implications rewrite physics at its core. If space-time is granular, then the Big Bang wasn't a singularity. It was a phase transition, like ice melting into water, where the quantum loops of pre-reality suddenly crystallized into the grid we inhabit. Even now, at scales too small to measure, space might still be flickering, its pixels adjusting in ways we can't perceive. Experiments hunting for space-time atoms in the faint whispers of gamma-ray bursts or the hum of gravitational waves could one day confirm whether we're truly living in a universe stitched together from these quantum threads. Until then, the math paints a mesmerizing portrait, reality as an infinite tapestry, its earliest threads still vibrating with the echoes of their first uncertain stitches. What if our universe wasn't born from nothing, but from the death throes of another cosmos, a black hole's final scream echoing into a new reality? This is the black hole quantum bounce theory, a spine-tingling idea that our entire existence might be the quantum afterbirth of a collapsed giant in some forgotten universe. Picture a cosmic Russian nesting doll where black holes aren't just destructive voids, but secret tunnels to new beginnings. When a black hole in some parent universe reached its limit, it didn't just vanish, it rebounded, its crushing singularity flipping inside out to become the Big Bang of our own cosmos. The math behind this is as elegant as it is bizarre. General relativity tells us black holes warp space-time into a one-way street where gravity's pull is so fierce even light can't escape. But loop quantum gravity, a rival to string theory, suggests there's no such thing as true infinite density. Instead, at the black hole's heart, quantum effects would cause a bounce, like a rubber band stretched to its limit before snapping back. In that moment of recoil, all the matter and energy the black hole devoured wouldn't be destroyed. It would be reborn, exploding outward as the seed of a new universe. Visualizing this is like watching a cosmic hourglass. On one side, a dying star collapses, funneling its essence into a black hole's narrow throat. But instead of hitting a dead end, that funnel pierces through to the other side, erupting into a firestorm of particles and radiation, our Big Bang. The parent universe's quantum state, imprinted in the black hole's structure, would bleed through, meaning our laws of physics might just be an inheritance from a long-dead ancestor cosmos. Here's where it gets even wilder. If black holes birth universes, then our own cosmos might be lousy with them. Every black hole formed in our universe, from stellar mass ones to the supermassive beasts at galactic centers, could each be incubating a new cosmos inside, invisible to us but teeming with their own stars, planets, and maybe even life. It's a fractal vision of reality, where universes stack within universes, each containing the seeds of countless others. Critics argue this skirts close to metaphysics. How could we ever peer beyond a black hole's event horizon to test the idea? But supporters point to eerie clues in our own universe. The cosmic microwave background, that fossilized glow of the Big Bang, shows puzzlingly uniform temperatures across regions that should never have been in contact. A quantum bounce could explain it. The pre-bounce black hole's crushing forces might have ironed out all wrinkles, leaving a smooth canvas for our universe to paint itself onto. Think of it as the ultimate cosmic recycling program. Death isn't an end, but a transformation. A black hole's collapse into a singularity becomes a new universe's explosive birth. And if that's true, then somewhere out there, in the depths of a supermassive black hole we'll never see, another version of us might be asking the same questions, unaware they're standing on the shoulders of giants who once stared into the abyss and found not darkness but the spark of everything. In the quantum haze of the early universe, particles and their mirror opposites, matter and antimatter, should have existed in perfect balance, annihilating each other in a flash of energy the moment they met. So why does anything exist at all? The answer might lie in a ghostly symmetry that once ruled the cosmos, a symmetry so flawless it bent the rules of reality itself. This is the supersymmetric seed theory, a radical proposal that the universe's first quantum state was governed by unbroken supersymmetry, a delicate equilibrium where every particle had a hidden twin and every force a perfect counterpart. Supersymmetry, or SUSY for short, isn't just a fancy idea, it's a mathematical lifeline for modern physics. It posits that every fermion, the building blocks of matter, like electrons and quarks, has a boson counterpart force carrying particles like photons and vice versa. In today's universe, these twins are nowhere to be found, suggesting supersymmetry is broken, a relic of a hotter, denser past. But rewind to the quantum phase of the early cosmos, and SUSY might have been in full swing, locking particles into a perfect dance where matter and antimatter were equally matched. Here's where the magic happens. As the universe cooled, that pristine symmetry would have fractured like ice on a pond, creating tiny cracks in the cosmic code. Visualize it like a spinning top while it's whirling fast. It stands perfectly upright, but as it slows, it wobbles, tipping in one unpredictable direction. In the quantum realm, this tipping could have favored matter over antimatter by the slimmest margin, perhaps just one extra particle in a billion surviving annihilation. Particle colliders like the Large Hadron Collider offer glimpses of this breaking act. When protons smash together at nearly light speed, they briefly recreate conditions akin to the early universe, spraying debris that hints at SUSY's shadowy remnants. Scientists hunt for superpartner particles, heavier, unseen twins of known particles that would cement supersymmetry's role in cosmic history. Though undiscovered so far, their absence might just mean they're too massive for current colliders to unmask, like fossils buried too deep for our shovels to reach. The stakes couldn't be higher. Without this asymmetry, the universe would be a featureless void, all matter and antimatter long since cancelled out. SUSY's subtle bias might be the reason stars, planets, and even we exist at all. It's a humbling thought that the entire tapestry of existence could hinge on a quantum hiccup in symmetry, a single note ringing louder than its echo in the primordial choir. And if colliders one day catch those elusive superpartners, it would mean we're not just studying the universe's laws, but eavesdropping on its very first conversation with itself. The universe's first quantum state might have left fingerprints, not in the stars or galaxies, but in the faint afterglow of creation itself. The quantum gravity wave trigger theory proposes that primordial ripples in space-time, born from the cosmos's earliest moments, acted like a cosmic hammer, shattering the superposition and locking reality into the form we recognize today. These aren't just any waves, they're gravity waves, distortions in the fabric of space-time so powerful they could have nudged the universe out of its quantum haze, imprinting their signature on the oldest light we can see, the cosmic microwave background. Think of the early universe as a pond frozen mid-ripple. Just as a stone tossed into water leaves concentric circles, the collapse of the quantum superposition might have sent shockwaves through space-time, freezing into the cosmic microwave background like whispers in cosmic amber. Scientists have already detected gravitational waves from black hole collisions, but these primordial waves would be different, stretching across the entire observable universe, their patterns etched into the heat map of creation. The cosmic microwave background isn't just a relic, it could be a quantum fossil, preserving the moment gravity itself helped choose the universe's fate. Here's where the evidence gets tantalizing. Telescopes like Planck have mapped the cosmic microwave background in exquisite detail, revealing subtle temperature variations, hotter and colder patches that form a kind of cosmic barcode. Some researchers argue these patterns aren't random. When they overlay theoretical gravity wave signatures onto these maps, certain anomalies line up eerily well. One stubborn hotspot near the constellation Eridanus, nicknamed the Cold Spot, has long puzzled astronomers. Could it be a scar from where a particularly strong gravity wave punched through the quantum fog, forcing a local collapse? Critics counter that the data is still too fuzzy to confirm anything. Gravity waves from the quantum era would be incredibly faint by now, their signals drowned in cosmic noise. But next-generation observatories, like the proposed Big Bang Observer space mission, aim to listen for these echoes directly. Imagine tuning a radio to the static between stations and catching, buried in the hiss, the faintest trace of a song, one that hasn't played for 13 billion years. That's the hunt for primordial gravity waves, an attempt to eavesdrop on the universe's first decisive moment. If confirmed, it would mean gravity isn't just a force that holds planets together. It's the cosmic sculptor that carved reality from quantum chaos. And those subtle wrinkles in the cosmic microwave background, they might be the brushstrokes of a universe choosing itself, a signature written in the language of space-time itself, waiting for us to decode it. What if the universe's quantum haze didn't collapse on its own? What if it took a nudge from the cosmos' most elusive inhabitants? The dark matter decoherence theory throws dark matter into the spotlight as the unsung architect of reality, proposing these invisible particles acted as nature's measuring device, forcing the early universe to pick a state. Picture dark matter not just as a gravitational scaffold for galaxies, but as a cosmic photographer, snapping the first definitive picture of existence when everything else was still a blur. We've long known dark matter outweighs normal matter 5 to 1, its gravity sculpting the universe's large-scale structure, but what if its role was even deeper? In quantum mechanics, any interaction with an external system can collapse a superposition, a process called decoherence. Most theories assume photons or other particles did the job, but dark matter's sheer abundance makes it a prime suspect. Imagine trillions of weakly interacting massive particles, or WIMP, drifting through the primordial quantum soup like invisible buoys. Each time one bumped into a quantum fluctuation, it could have acted like a tiny observer, incrementally chiseling uncertainty into concrete reality. The parallels to modern WIMP detectors are uncanny. Today, scientists hunt for dark matter by waiting for it to collide with normal matter in ultra-sensitive, deep underground experiments. These detectors work because even the faintest interaction leaves a trace, a blip of energy where the invisible becomes briefly seen. Scale this up to the early universe and dark matter halos, those vast, diffuse clouds enveloping galaxies, might be fossilized evidence of this measuring process. The universe didn't just wake up one day and choose a state. It was probed into existence one weak interaction at a time. Here's where the theory gets thorny. If dark matter caused decoherence, why didn't it happen instantly? Supporters argue it was a cascade, a growing avalanche of interactions that started locally and spread. Visualize ink dispersing in water, first a few tendrils, then an unstoppable wave. Early pockets of reality might have crystallized around dark matter concentrations, their influence expanding until the whole cosmos snapped into focus. The voids between galaxy clusters, those eerily empty regions, could be the last holdouts where quantum fog lingered longest. Critics ask, how can something we've never directly observed be responsible for defining reality? It's a fair point, but the math hints at dark matter's unique qualifications. Unlike photons, which were trapped in a hot, opaque plasma early on, dark matter could move freely, its particles threading through the universe like needles stitching a quilt. And if dark matter interacts with itself, as some models suggest, those interactions might have amplified its decoherence power, turning it into a quantum bulldozer smoothing out the primordial chaos. Whether this theory holds or not, it reframes dark matter from a passive backdrop to an active participant in creation. Those ghostly halos aren't just holding galaxies together, they might be the reason galaxies exist at all. And if future experiments finally catch a wimp in the act, we might not just be discovering a particle. We could be uncovering the universe's first witness, the silent observer that watched reality take its first breath. The very fabric of space-time might hold a secret far stranger than we realize, a phantom energy field so powerful it didn't just stretch the universe outward, but reached back in time to shape its own birth. This is the phantom energy collapse theory, where the same mysterious force driving the cosmos's runaway expansion today could have played a pivotal role in snapping the early universe out of its quantum fog. Picture a cosmic tug-of-war, phantom energy, this repulsive gravity on steroids, relentlessly pushing space apart while the nascent universe teetered between infinite possibilities. Then, in a flash, the balance tipped not toward destruction but toward definition. Phantom energy isn't just hypothetical dark energy, it's dark energy's wilder, more volatile cousin. While ordinary dark energy accelerates expansion at a steady pace, phantom energy grows stronger over time, threatening to one day rip apart atoms themselves in a Big Rip scenario. But rewind to the universe's first moments, and this terrifying force might have been the midwife of reality. In the quantum haze, phantom energy could have acted like a cosmic sculptor, its relentless pressure warping the fabric of superposition until certain states became untenable. Imagine blowing up a balloon covered in wet paint. The stretching surface would thin and crack, forcing the paint to separate into distinct patterns. Similarly, phantom energy's pull might have fractured the quantum foam, isolating stable configurations from the noise. The math behind this is as elegant as it is unsettling. Quantum fields and phantom energy share a cryptic link, both thrive on negative pressure. In the early universe's dense plasma, phantom energy's repulsive gravity could have amplified quantum fluctuations, turning microscopic ripples into macroscopic landmarks. Visualize inflationary bubbles, not just regions of rapid expansion, but quantum domains where phantom energy's grip was strongest. These bubbles wouldn't merely grow, they'd select, their expansion favoring certain quantum states over others, like a cosmic version of survival of the fittest. The result, a universe where the regions that crystallized first were the ones where phantom energy's push and quantum stability found an uneasy truce. Clues to this might lurk in the universe's large-scale structure. If phantom energy sculpted reality, its fingerprints could be etched into the distribution of galaxy clusters, those vast cosmic webs that trace the universe's skeleton. Certain anomalies, like the mysterious cold spot in the cosmic microwave background, could be scars from where phantom energy's influence was particularly fierce, a patch of space where the quantum dice rolled decisively. Even dark flow, the controversial observation that some galaxy clusters seem to drift in a preferred direction, might hint at phantom energy's early asymmetry, a relic of the moment it tipped the scales toward the reality we know. But here's the twist: if phantom energy was present at creation, it never left. It's still here, lurking in the void, stretching the cosmos toward an uncertain fate. The same force that might have collapsed the universe's quantum haze is now accelerating its expansion, a cosmic pendulum swinging from creation to dissolution. This duality raises a haunting question. Did reality emerge because of phantom energy, or is it merely postponing the inevitable? The answer might lie in the quantum echoes still vibrating through space-time, whispers of a beginning shaped by the very force that could one day unmake it all. Among the countless particles zipping through the cosmos, neutrinos might hold the most surreal resume: ghostly, nearly massless entities that barely interact with matter, yet so abundant they outnumber atoms 1,000,000,000 to 1. Now imagine these cosmic phantoms playing an even stranger role. As the universe's first observers, the silent witnesses whose fleeting interactions collapse the primordial quantum haze into reality. This is the neutrino consciousness hypothesis, a theory so audacious it blurs the line between particle physics and science fiction, suggesting that neutrinos, through their very existence, measured the early universe into being. Neutrinos are nature's ultimate enigmas. Born in the hearts of stars and supernova, they pass through entire planets like light through glass, with trillions streaming through your body every second without a trace. But here's the twist: they oscillate. As they travel, neutrinos morph between three flavors: electron, muon, and tau, a quantum identity crisis that implies they're constantly interacting with something, even if we can't see it. In the early universe's dense, hot plasma, these oscillations might have been far more frequent, turning neutrinos into a bustling quantum audience, their every subtle shift acting like 1,000,000,000,000 tiny measurements nudging superposition toward certainty. Now the sci-fi kicker: what if neutrinos weren't just passive players but somehow sentient? Before you dismiss this as fringe fantasy, consider the scale. With neutrinos outnumbering atoms so vastly, even a minuscule fraction exhibiting complex behavior could form a cosmic network of awareness. Philosophers have long pondered panpsychism, the idea that consciousness is a fundamental property of matter. If even a sliver of that applies here, neutrinos could have been the universe's first thinkers, their collective interactions not just collapsing quantum states but choosing them. Picture a cosmic game of 20 questions, where reality emerges from an invisible dialogue between particles we barely understand. Critics, unsurprisingly, pounce on the lack of mechanism. How could a particle with no charge and almost no mass harbor consciousness? Yet supporters point to eerie parallels in quantum biology. Some theories suggest microtubules in brain cells might harness quantum effects. Could neutrinos, with their oscillations, be doing something similar on a universal scale? And if consciousness is just integrated information, as some models posit, then a neutrino's ability to remember its flavor shifts might qualify as a primitive form of cognition. The echoes of this might linger today. If neutrinos helped shape reality, their oscillations could have imprinted patterns in the cosmic microwave background or the distribution of dark matter. Experiments like IceCube, buried in Antarctic ice, are already catching high-energy neutrinos from distant galaxies. Could their behavior hint at deeper, older roles? It's a long shot, but in a quantum universe, even the wildest possibilities can't be ruled out. After all, if a ghost particle can pass through a star unscathed, who's to say it didn't once help build the cosmos itself? What if the universe's first quantum state wasn't just a chaotic soup of particles, but a cosmic supercomputer, hardwired to calculate its own existence? The quantum Turing universe theory takes inspiration from Alan Turing's visionary work and scales it to cosmic proportions, suggesting the early cosmos wasn't just governed by physics but by algorithms. Picture the Big Bang not as an explosion, but as the universe booting up, its quantum fluctuations humming with the primal logic of a program writing its own code. At the heart of this idea lies a radical equivalence. Every quantum event can be modeled as a computation. Just as a classical computer flips bits between 0 and 1, the universe's quantum fields toggle between states, processing information at scales we can barely fathom. In those first moments, space-time itself might have been a lattice of qubits, quantum bits that exist in superpositions of both 0 and 1. Each one a pixel in the fabric of reality, flickering with potential until the cosmic program executed its first decisive operation. Think of it like a game of quantum Sudoku. At the start, every cell, every qubit holds every possible number simultaneously. But as the rules of physics solve constraints, certain configurations stabilize, collapsing possibilities into definite values. The universe's initial quantum haze, that's the puzzle mid-calculation. The galaxies, stars, and atoms we see today, they're the output, the solved grid after 13 billion years of cosmic processing. The implications rewrite how we view complexity. Computational theory classifies problems by how hard they are to solve. Some take milliseconds, others longer than the universe's lifespan. If the early cosmos was a quantum computation, then the structure we see might reflect its computational class, the inherent difficulty of resolving its own quantum state. Simple, stable configurations like hydrogen atoms could be the universe's easy solutions, while black holes or dark matter might represent stubborn, unsolved subroutines still running in the background. Visualizing this demands a shift in perspective. Animations of the early universe often show swirling particles or exploding fireballs, but what if we depicted it as a cascading grid of qubits, their entangled states flashing like city lights as logic gates flick open and shut? Certain patterns would emerge: clusters of stability matter, regions of unresolved complexity, dark energy, even errors in the cosmic code, quantum anomalies we can't yet explain. Critics argue this leans too heavily on metaphor after all. Who or what is the universe computing for? But proponents point to eerie parallels in quantum gravity. In some models, space-time's granularity, its pixel-like structure at microscopic scales, mirrors the discrete steps of a Turing machine. Even black holes, those cosmic enigmas, might function like natural quantum computers, their event horizons encoding information in ways that eerily resemble error-correcting codes in human-made systems. Whether the universe truly is a quantum computer remains an open question. But if even a sliver of this theory holds, it means reality isn't just governed by math, it is math unfolding in real time. Every particle collision, every galaxy spinning in the void could be part of a computation so vast, its final answer might simply be existence itself. And if that's true, then we're not just observers of the cosmos, we're patterns in its output, temporary variables in a program that's been running since the first qubit flickered to life. What if the universe's quantum foam wasn't just random noise, but a cosmic fractal, an infinite cascade of self-repeating patterns stretching from the smallest quantum flicker to the vast web of galaxies? The fractal quantum foam theory takes inspiration from the swirling, recursive beauty of Mandelbrot, sets those mesmerizing mathematical shapes where every zoom reveals identical structures nested within structures, and applies it to the very fabric of reality. Picture the early universe not as a turbulent sea, but as an intricate snowflake, its quantum fluctuations echoing the same geometric whisper at every scale, from Planck-length ripples to the birth of superclusters. Fractals are nature's favorite blueprint. From the branching of trees to the jagged coastline of continents, self-similar patterns emerge everywhere when complexity unfolds under simple, repeating rules. Now imagine those rules written into the universe's first quantum state. At the tiniest scales, fluctuations in the quantum foam wouldn't be chaotic. They'd be microcosms of the larger structures they'd eventually form. A spiral of energy here mirrors the whirl of a galaxy there. A knot of space-time here echoes the tangled filaments of dark matter there. It's as if the cosmos was encoded with a fractal algorithm, a cosmic copy and paste command running on loop until reality solidified. The math behind this is as breathtaking as it is precise. Fractal geometry thrives on feedback loops, tiny variations magnified over iterations. Apply this to quantum field theory, and those fluctuations in the early universe could have iterated like a cosmic kaleidoscope, their patterns scaling up flawlessly. Visualize it like a 3D printer building a universe layer by layer, where each layer, no matter how small or large, bears the same intricate signature. The cosmic microwave background, that snapshot of the infant universe, might even hide these fractal fingerprints in its temperature variations, subtle harmonics of a pattern too vast to see all at once. Here's where it bends the mind. If the quantum foam was fractal, then superposition wasn't just a blur of probabilities, it was a symphony of nested possibilities. Zoom in on a single quantum event, and you'd find the same interplay of uncertainty playing out in miniature, like a hall of mirrors reflecting possibilities within possibilities. This could explain why the universe looks eerily similar at vastly different scales, from the spin of electrons to the orbits of planets. The rules don't change because they're written in fractal ink, repeating their logic from the quantum to the cosmic. Clues might lurk in the voids between galaxies. These vast, empty regions aren't randomly scattered, they're arranged in bubble-like structures that some simulations suggest could be fractal remnants. Even black holes, those paradoxical beasts, might obey fractal thermodynamics, their event horizons encoding information in self-similar layers. The more we look, the more the universe seems to whisper, "I am recursive." I repeat, yet the theory isn't without skeptics. Fractals are beautiful, but are they necessary? Could the universe's large-scale structure emerge from simpler randomness? Maybe, but then why do so many natural systems, from lung vessels to lightning bolts, default to fractal elegance? The answer might lie in efficiency. Fractals maximize complexity with minimal rules, a cosmic cheat code for building a universe that's rich, stable, and strangely familiar no matter how closely you look. Picture the quantum foam as a cosmic tapestry woven with infinite threads, each thread a smaller version of the whole. In those first moments, the universe wasn't just choosing a state, it was unfolding a pattern, a blueprint that would repeat itself forever. And if that's true, then every star, every atom, every fleeting quantum flicker is still humming that original fractal tune, a song written in the language of scales within scales. In the quantum chaos of the early universe, where every particle's identity flickered between possibilities, there might have been a hidden player pulling the strings, not a particle we've seen, but one we've only dreamed of, the magnetic monopole. Picture a cosmic magnet with just one pole, a north without a south or vice versa, a hypothetical beast that's eluded physicists for decades, yet could hold the key to why reality solidified the way it did. The magnetic monopole measurement theory proposes these elusive entities didn't just exist in the primordial soup. They were the universe's first referees, their very presence forcing the quantum haze to pick a side. Paul Dirac first theorized monopoles in the 1930s, showing how their existence would neatly explain why electric charge comes in tidy, discrete units. But in the seething heat of the early cosmos, monopoles might have done more than balance equations. They could have been quantum collapse catalysts. Unlike familiar particles, which carry both north and south magnetic poles, monopoles would have interacted with the universe's magnetic fields in a unique, asymmetrical way. Every fleeting brush between a monopole and a quantum fluctuation might have acted like a cosmic coin toss, skewing probabilities until certain states became inevitable. Imagine a room filled with spinning tops, each wobbling in every direction at once, then dropping in a handful of magnets that only attract one pole. Suddenly, the tops aren't just spinning, their aligning, their chaos funneled into order by an invisible hand. Artistic renditions of monopoles often show them as shimmering, needle-like structures piercing through space, trailing twisted magnetic field lines like cosmic thread. In the early universe, these needles might have woven the first stable patterns into the quantum fabric. As monopoles threaded through the plasma, their one-way magnetism could have polarized nearby particles, creating domains where certain quantum states froze faster than others. Over time, these patches of stability would have merged, stitching together the universe we recognize. The cosmic microwave background's faint anisotropies, those subtle hot and cold spots, might even be scars from where monopoles left their mark like fingerprints on a frosted window. The hunt for monopoles isn't just academic fantasy. Experiments like the Mo-Edel detector at CERN are scouring high-energy collisions for traces of these phantom particles, while cosmic ray observatories scan the skies for their ancient signatures. If monopoles are out there, lurking in the cosmos or trapped inside dense celestial bodies, their discovery wouldn't just fill a gap in particle physics, it might rewrite the story of how reality chose its form. Dirac once called monopoles a window into the quantum world, but they could be more than a window. They could be the hinge it swung open on, the silent architects of a universe that until they measured it could have been anything at all. Deep in the quantum equations of particle physics lurks a mystery so subtle, most of the universe seems to ignore it, the strong CP problem. Why does the force binding atomic nuclei so perfectly respect symmetry between matter and antimatter, when every other fundamental force cheats just a little? The answer might lie in a ghostly field permeating the cosmos, not just solving this decades-old puzzle, but potentially shaping the universe's first quantum state. Enter actions, hypothetical particles so lightweight and shy they've been called quantum snowflakes, drifting unseen through the cosmos. The action field collapse theory proposes these elusive entities didn't just emerge after the Big Bang, they catalyzed it, their collective settling from quantum haze into definite states, acting as a cosmic snow globe shaken, then stilled, leaving reality crystallized in its wake. Actions were first dreamed up to salvage symmetry in quantum chromodynamics, the math governing quarks and gluons. Without them, the equations suggest the strong force should warp matter and antimatter slightly differently, yet we've never detected such a distortion. Actions elegantly patch this hole by introducing a field that automatically resets the imbalance to zero, like a cosmic thermostat fine-tuning itself. But here's where it gets cosmic. If actions exist, they wouldn't just be passive fixers, they'd be quantum dominoes. Their field would have permeated the early universe's superposition, a lattice of potential waiting to snap into alignment. Picture a blizzard in zero gravity, where every snowflake hovers motionless until the slightest tremor sends each one tumbling into place. That tremor. The universe's first irreversible choice. Visualizing this is like watching frost spread across a window pane. At first, the quantum action field would have been a shimmering fog of possibilities, every potential configuration overlapping. But as the cosmos expanded and cooled, this fog would have condensed not into water droplets, but into a crystalline structure of action, snow, each flake locking into orientation with its neighbors. This phase transition wouldn't just solve the strong CP problem. It could have been the universe's first decisive measurement, breaking the symmetry of superposition by anchoring quantum uncertainties to the action field's emerging order. Regions where actions aligned one way might have favored matter over antimatter, others the reverse. Our universe's overwhelming tilt toward matter could be a fossil of this snowfall, a drift of cosmic flakes that happen to land up rather than down. Experiments like the Action Dark Matter E-experiment are already hunting these particles by bathing magnetic fields in microwave cavities, hoping to catch an action's faint conversion to a photon. If they succeed, it won't just confirm a new particle, it'll unveil a sculptor of reality. Because actions aren't just snowflakes in the cosmic storm, They might be the reason the storm calmed at all, their quiet symmetry breaking the hand that steadied the quantum dice. And if that's true, then the universe we know isn't just built on atoms and forces. It's built on the silent, delicate ballet of particles we've yet to see, whose first delicate steps may have written the laws we now take for granted. Among the most audacious theories of the quantum dawn is the idea that space-time didn't just smooth itself out. It was stitched together by cosmic shortcuts, threads of reality so warped they turned inside out. This is the quantum wormhole bridge hypothesis, where the universe's first moments were stabilized not by particles or forces, but by a labyrinth of microscopic wormholes, each one a frayed end of space-time knotted back onto itself. Picture the early cosmos as a tangled ball of quantum yarn, with Einstein-Rosen bridges, those theoretical tunnels through space-time acting as the needles that wove chaos into order. Wormholes aren't just sci-fi fodder. Einstein's equations allow for them, though they're notoriously unstable, snapping shut faster than they form without exotic matter to prop them open. But in the quantum froth of the early universe, stability might not have been necessary. Entanglement, that spooky quantum connection linking particles across vast distances, could have acted as cosmic glue, binding the mouths of these wormholes together even as space-time buckled and stretched around them. Visualize two black holes born from the same quantum fluctuation, their event horizons connected by an invisible thread. Now scale that up to countless pairs, a network of bridges stitching the quantum haze into a coherent fabric. Here's where the math gets mesmerizing. Quantum entanglement and wormholes might be two sides of the same coin. The ER equals EPR conjecture, a brainchild of physicists Juan Maldeisner and Leonard Susskind, suggests that every pair of entangled particles is linked by a microscopic wormhole, not in the traditional sense, but as a geometric manifestation of their quantum bond. In the early universe, these bonds wouldn't have been rare. They'd have been the rule, with every fluctuation spawning new entangled pairs and, by extension, new wormholes. The result, a self-reinforcing web of quantum tunnels, each one shuttling information and energy just fast enough to keep the cosmos from tearing itself apart. The echoes of this might linger in the cosmic microwave background. If wormhole bridges stabilized the universe's infancy, their gravitational shadows could have imprinted faint circular patterns, bruises, in the afterglow where space-time pinched into tunnels. Some researchers even speculate that dark matter's elusive pull could be the ghostly tension of these ancient bridges, their massless throats still humming with the resonance of a quantum network that once held everything together. Yet skeptics ask, if this web existed, why didn't it collapse under its own instability? The answer might lie in the universe's rapid expansion. Inflation, that split-second stretch of space-time, could have frozen the wormholes in place, locking them into a cosmic lattice before they had time to dissolve. Like bugs in amber, these bridges would have fossilized, their entanglement decaying over eons into the weaker quantum links we see today. Imagine the universe's first moments not as a fireball, but as a quantum cat's cradle with wormhole threads pulled taut between the fingers of reality. Every galaxy, every star might owe its existence to this primordial knitting, a tapestry of tunnels that stitched uncertainty into structure. And if those threads still hum beneath the surface of space-time, they're not just relics, they're the hidden scaffolding of reality itself, waiting for us to tug on the right string. What if time itself wasn't a fundamental force, but an illusion spun from something far more primal: temperature? The thermal time hypothesis flips our understanding of causality on its head, proposing that the universe didn't just have a timeline, it chose one, guided by the erratic dance of heat and cold in the quantum haze. Picture the early cosmos not as a ticking clock, but as a feverish dream, where regions of high and low energy flickered like static on an old TV screen. In this chaos, certain thermal patterns might have acted like cosmic conductors, orchestrating the collapse of quantum probabilities into the steady rhythm of cause and effect we call time. At its core, this theory reimagines time as an emergent property, a side effect of thermodynamics rather than a stage for it. Normally, we think of time as the backdrop against which entropy increases, the arrow that points inexorably from order to disorder. But in the thermal time hypothesis, that arrow isn't built into the universe's fabric. It's a byproduct of local thermal gradients. Imagine pouring hot coffee into a cold cup. The heat spreads, the temperatures equalize, and this irreversible flow creates the illusion of time's direction. Now scale this up to the quantum foam of the early universe, where every fluctuation was a microscopic cup and coffee, a patch of imbalance seeking equilibrium. The regions where heat flowed most predictably could have become the scaffolding for our timeline, while others dissolved back into noise. Visualizing this demands a shift in perspective. Artistic renditions might depict the infant universe as a shimmering heat map, with pockets of red and blue representing hotter and colder quantum states. Where these regions brushed against each other, their thermal differences didn't just transfer energy, they etched the first grooves of causality, like a needle carving spiral tracks into a vinyl record. Over eons, these grooves deepened into the unshakable before and after we take for granted. The cosmic microwave background, that fossilized glow from the Big Bang, might even hide traces of this thermal fingerprint, subtle asymmetries where the universe's first hot and cold decided which probabilities survived. Critics argue this leans too heavily on analogy. Can temperature really create time or just describe it? Yet labs are already teasing out clues. In quantum systems cooled to near absolute zero, entropy sometimes behaves bizarrely, with particles appearing to remember their thermal past in ways that defy classical intuition. If microscopic systems can blur time's arrow, why couldn't the primordial universe have woven it entirely from scratch? The stakes are cosmic. If time is truly born from thermal whispers, then black holes, where temperatures soar and space-time warps beyond recognition, might not just bend time. They could unmake it, unraveling causality at their edges like threads plucked from a sweater. Even dark energy's accelerating expansion takes on new meaning, not just stretching space, but quietly rewriting the thermal rules that ground time itself. So the next time you check your watch, consider this. Those ticking seconds might not be fundamental. They could be echoes of a deeper, older rhythm, the universe's first fever breaking, its sweat cooling into the structure of reality. And if that's true, then time isn't the canvas of existence, it's the painting. The early universe might have been knotted into existence, not by particles or forces, but by cosmic scars so deep they're unraveling sculpted reality itself. The topological defect decay theory suggests that exotic structures, cosmic strings, textures, or domain walls lace through the quantum haze like flaws in a crystal, their tension twisting superposition into stability. Picture space-time not as a smooth fabric, but as a tangled necklace, its threads strained by invisible defects left over from the cosmos's violent birth. When these imperfections finally decayed, their collapse didn't just release energy, it may have been the hammer blow that shattered quantum ambiguity, forging the galaxies we see today. Cosmic strings aren't mere hypotheticals, they're fractures in space-time. Hypothetical one-dimensional relics thinner than a proton, but with the mass of a mountain range per inch. Born from phase transitions in the early universe, like cracks forming in ice as it freezes, these defects would have carried unimaginable tension, vibrating like galactic-scale guitar strings. In the quantum fog, their vibrations could have acted as a tuning fork, resonating with certain probabilities while damping others. Visualize a spiderweb trembling in the wind. Certain frequencies amplify, others fade. Cosmic strings might have done the same to the universe's superposition, their oscillations selecting which quantum states survived by sheer mechanical resonance. Textures add another layer of strangeness. Unlike strings, these are three-dimensional kinks in the quantum fields, regions where the universe's symmetry breaking froze imperfectly, like a mosaic with tiles slightly askew. As the cosmos expanded, textures would have strained against their own topology, eventually collapsing in bursts of energy. Simulations suggest these bursts could have seeded the first density fluctuations, tiny overdensities that later grew into galaxies. The eerie part, the pattern of galaxy clusters we see today, might trace the skeleton of these long-vanished defects, their ghostly imprint woven into the cosmic web. Here's where the math becomes poetry. Topological defects don't just decay randomly, they unwind in cascades like a knotted rope shaking itself loose. Each unraveling step releases energy, but also information, a kind of cosmic Morse code etched into the fabric of space. As defects decayed, they could have transferred their topological memory to the surrounding quantum fields, forcing coherence in regions that were once probabilistic fog. Imagine dropping dye into a whirlpool. The vortex's structure dictates how the color spreads. Similarly, cosmic strings and textures might have channeled the universe's quantum uncertainty into orderly currents, their death throes spinning chaos into structure. The echoes of this might be hiding in plain sight. If topological defects sculpted the early universe, their fingerprints could linger in the polarization of the cosmic microwave background, subtle swirls in the ancient light betraying where space-time once knotted and snapped. Even dark matter's elusive distribution could hold clues, as defects' gravitational shadows may have funneled invisible particles into the filaments we observe today. Future telescopes, like the Square Kilometre Array, could hunt for these signatures by mapping the universe's large-scale structure with unprecedented precision, searching for the faint scars of a cosmos that untangled itself into being. Yet the most tantalizing possibility isn't just how defects shaped reality, it's that they might still exist. Cosmic strings, if real, could stretch across the observable universe even now, their ancient vibrations subtly warping the light of distant quasars or lensing galaxies into strange double visions. Discovering one would be like finding the brushstrokes of a painter who vanished billions of years ago, their handiwork frozen in the canvas of space-time. And if textures or domain walls persist in some form, they could be the universe's ultimate fossils, not relics of a dead past, but active participants in a story still being written, their final unwinding yet to come. Whether long vanished or still lurking, topological defects remind us that reality's birth wasn't gentle. It was a storm of geometry and chance where flaws became features, and the universe's deepest wounds may have been the very seams that held it together. What if the universe's first quantum state wasn't determined by cold, impersonal math, but by something far more intimate, perspective? The quantum Bayesian beginning theory, or cubism, takes one of the most radical interpretations of quantum mechanics and scales it to cosmic proportions, suggesting reality didn't solidify until something began interpreting it. Unlike traditional theories where probabilities collapse via mysterious mechanisms, cubism flips the script. Probabilities aren't properties of the world, but of the observer's belief. Picture the early universe not as a ticking clockwork, but as a cosmic Rorschach test, its ink blot of possibilities only resolving when a viewpoint emerged to give it meaning. At its heart, cubism treats quantum mechanics less like a lawbook and more like a language, a way for agents, whether humans, animals, or future AI, to navigate uncertainty. In labs, this means a particle's spin or position isn't real until an experimenter assigns credence to it. Now stretch this back to the Big Bang. The universe's quantum fog wasn't just a haze of overlapping states, it was a canvas waiting for the first brushstroke of interpretation. Who wielded that brush? Supporters propose a spectrum of answers, maybe a primitive quantum observer, like a self-replicating molecule in an infant cosmos, or perhaps the universe itself, bootstrapping observation through sheer complexity. Visualizing this demands a shift from physics to phenomenology. Imagine an animation where the early universe pulses with potential swirls of color representing superpositioned galaxies, stars, laws of physics, all shifting like a kaleidoscope. Then a faint glow emerges, the first observer, even if just a rudimentary quantum system capable of interaction. Where its attention falls, the blur resolves into structure like fog lifting under sunlight. Distant regions, untouched by any perspective, remain probabilistic ghosts. It's not that they don't exist, they're waiting for their turn to be seen. Critics pounce on the solipsistic overtones. Does this reduce reality to a patchwork of subjective bubbles? Cubists counter that shared experience emerges from overlapping perspectives, like neighbors agreeing on the weather while disagreeing on its beauty. The cosmic microwave background's uniformity might not reflect an objective early universe, but a consensus among countless entangled observers, their collective attention ironing out contradictions. Yet the most provocative implication isn't about the past, it's about the future. If the universe requires observers to crystallize, then the arrow of time might point toward increasing interpretation. Each act of measurement, from a photon hitting a retina to a telescope capturing starlight, isn't just recording reality, it's completing it. In this view, the Big Bang wasn't a beginning but an invitation, one we're still answering, one observation at a time. In the swirling quantum chaos of the early universe, there may have been an invisible sculptor at work. A field so pervasive it gives mass to everything it touches, yet so subtle we only confirmed its existence in 2012. The Higgs field, famous for its boson particle discovery, might have played a far wilder role than we imagined, not just shaping matter but deciding what matter would be. Imagine this cosmic field not as a passive backdrop, but as a quantum referee in the universe's earliest moments, its fluctuations acting like snowfall on a pond, each flake freezing superpositions into solid reality as they landed. The Higgs mechanism is often described as a cosmic molasses, a field that particles move through, gaining mass like swimmers trudging through honey. But rewind to the universe's quantum dawn, and this molasses might have been more like a blizzard. As the cosmos cooled, the Higgs field underwent a phase transition, shifting from a high-energy state to its current, quieter configuration. This shift, called spontaneous symmetry breaking, didn't just give particles mass, it could have been the universe's first irreversible decision. Visualize a snowy landscape where every drifting flake is a Higgs boson condensing out of the quantum foam. Where they settled, probabilities collapsed. Regions rich in Higgs snow locked particles into their observed masses and properties, while areas still in flux remained probabilistic fog, the boundary between these zones. That's where reality crystallized, one frozen flake at a time. Here's where quantum mechanics tangles with cosmology. In the lab, we see particles interacting with the Higgs field like actors taking the stage, their masses determined by how strongly they feel its presence. But in the early universe's superposition, particles weren't just on stage, they were everywhere on it at once. The Higgs field's phase transition didn't just assign masses, it chose which configurations of those particles would survive decoherence. Think of it like a cosmic game of musical chairs. When the Higgs music stopped, only the particles sitting in stable configurations won, becoming the protons, electrons, and neutrinos we know. The rest they dissolved back into quantum noise, their potential unrealized. The echoes of this might linger in the cosmos today. The Higgs field's uneven settling could explain why matter clusters the way it does, why galaxies gather along filamentary scaffolds, as if drawn toward regions where the quantum snow fell thickest. Even dark matter's elusive nature might trace back to this process. If certain particles interacted too weakly with the Higgs, they'd have been left floating in the probabilistic fog, never fully collapsing into the visible universe's structure. Experiments at the Large Hadron Collider offer tantalizing glimpses into this primordial snowfall. When physicists smash protons together at near light speeds, they briefly recreate the energy soup of the early universe, watching as Higgs bosons blink into existence and decay. The patterns of these decays, how often certain particles appear, could reveal how the Higgs field's preferences shaped reality's menu. Some models even suggest the Higgs could exist in multiple metastable states, meaning our universe's particular flavor of physics might just be one possibility among many, a single frost pattern on a window with infinite others waiting to form. Picture the infant universe as a pond on the cusp of freezing. The Higgs field is the first delicate ice crystal forming on the surface, a tiny, local event that spreads unpredictably, branching into fractal patterns as it goes. Where the ice thickens, reality solidifies. Where it stays liquid, quantum possibilities still churn. And if we're reading the clues right, we're not just studying the ice, we're living in its cracks. Every atom in our body's a testament to where the snow fell just right. At the heart of some of the universe's densest objects might lie the answer to one of its earliest mysteries. The strange vibrations of neutron stars could be echoes of the quantum collapse that birthed reality itself. Imagine a cosmic tuning fork forged in the unimaginable pressures of a collapsed stellar core, ringing with frequencies so precise they make atomic clocks look crude. These aren't just celestial oddities, they might be relics of the universe's first decisive moment, when the quantum fog solidified into the world we know. Neutron stars are nature's most extreme laboratories, packing more mass than the Sun into a sphere the size of Manhattan. Their crust's crystalline surfaces, harder than diamond, vibrate under the strain of unimaginable gravity, sending ripples through space-time itself. But here's the twist, those vibrations aren't random. Like the grooves on a vinyl record, their patterns could encode information about the universe's earliest quantum state. When a neutron star forms, its crust freezes into a lattice so dense it forces protons and electrons to merge into neutrons, a process eerily reminiscent of how quantum probabilities choose definite states during collapse. Could the same physics be at play? Pulsars, rapidly spinning neutron stars that beam radiation like cosmic lighthouses, offer a clue. Their precise pulses, some accurate to microseconds over centuries, suggest an underlying order deeper than mere mechanics. Simulations show that when neutron star crusts fracture under stress, they emit gravitational waves in distinct frequencies, like a bell struck by a hammer. Now imagine those frequencies superimposed onto the quantum foam of the early universe. Certain vibrations would resonate with specific superpositions, amplifying them while damping others. It's like blowing on a dandelion. Some seeds catch the wind, others fall away. The universe's structure might trace back to these cosmic harmonies, its galaxies, and voids, the notes left behind. Visualizing this is easier with sound. Convert a pulsar's electromagnetic pulses into audio, and you get an eerie, rhythmic clicking like a cosmic Geiger counter. Now slow those clicks down 1,000-fold, and hidden beneath the noise emerge deep, resonant tones, frequencies that match theoretical models of the early universe's quantum oscillations. The overlap is startling. Both systems' neutron star crusts and the primordial quantum field seem to vibrate at scales governed by the same fundamental constants. Coincidence or evidence of a deeper connection where the universe's first measurement was less an observation than a vibration, a standing wave that froze probabilities into reality? Critics argue this stretches analogy too far. After all, neutron stars formed billions of years after the Big Bang, but supporters counter that the underlying physics might be universal. Just as a single equation describes sound waves in air and ripples on a pond, the same quantum principles governing neutron star vibrations could have operated in the early cosmos, scaled up to universe-spanning proportions. The key lies in symmetry. Both systems are governed by the strong nuclear force, the same glue that binds quarks into protons and neutrons. If that force left fingerprints in the neutron star's oscillations, might those same prints be smeared across the cosmic microwave background? Experiments are already hunting for these echoes. Gravitational wave detectors like LIGO and future pulsar timing arrays aim to decode neutron star vibrations with unprecedented precision. If their data reveals patterns matching predictions from quantum cosmology, It would mean these stellar corpses aren't just endpoints, they're cosmic Rosetta Stones, whispering the universe's first language. And if we learn to listen, we might finally hear how the silence of superposition broke into the symphony of existence. Somewhere in the faint ripples of spacetime detected by LIGO laser beams might be hiding whispers from the universe's very first moment, not just the aftereffects of colliding black holes, but ghostly echoes of when reality itself was still trembling between possibilities. The quantum gravity echo theory proposes that gravitational waves don't just carry information about cosmic cataclysms happening now. They could be inscribed with relics of the primordial superposition, subtle distortions in the fabric of spacetime that trace back to the instant before the quantum haze collapsed. Think of it like tuning into a cosmic radio station where most signals come from predictable sources, stellar explosions, neutron star mergers, but buried in the static are older, weirder transmissions. When LIGO detects a gravitational wave, its signature is typically clean. A rising chirp as two massive objects spiral inward, then a ring down as they merge. But overlay enough of these events, and some show anomalies, tiny fluctuations in frequency or amplitude that don't match simulations. Mainstream astrophysics writes these off as noise or instrument glitches, but what if there's something far stranger? Quantum gravity, the long-sought marriage of general relativity and quantum mechanics, predicts spacetime itself should have a granular structure at microscopic scales, a foam-like texture where tiny wormholes and quantum fluctuations pop in and out of existence. In the early universe, this foam wouldn't have been microscopic, it would have been universal, with the entire cosmos seething with quantum turbulence. As reality crystallized, most of that turbulence would have smoothed out, but not all. Some imprints might have frozen into spacetime like fingerprints in cooling glass, stretching and thinning as the universe expanded but never fully disappearing. Now imagine a gravitational wave from a black hole collision passing through one of these ancient wrinkles. Like a ripple crossing a pond with a barely submerged log, its shape would distort in subtle ways, not enough to erase the main signal, but enough to leave a faint quantum accent in the data. These distortions wouldn't follow classical physics, they'd carry the hallmarks of quantum randomness, unpredictable spikes or dips that correlate across multiple detections. The challenge, teasing them out from the noise. Here's where the hunt gets electrifying. Scientists are already developing algorithms to search LIGO data for these anomalies, using techniques from quantum field theory to model how primordial spacetime defects would affect passing waves. One approach treats the early universe like a vast quantum drumhead. Its first gravitational waves weren't clean tones, but a cacophony of overlapping frequencies, like a chord struck on a piano where every key is pressed at once. As the cosmos expanded, most of these frequencies redshifted into undetectability, but some might persist as interference patterns, subtly modulating the gravitational waves we see today. The implications are staggering. If confirmed, these echoes wouldn't just be cosmic background noise, they'd be a direct line to the universe's quantum infancy, a snapshot of reality before it chose its form. Future observatories like the Einstein telescope or space-based LISA could amplify the signal, their ultra-precise instruments tuned to catch whispers older than stars. We might finally glimpse the quantum gravity regime not through particle colliders or telescopes, but by listening to spacetime itself vibrate with memories of its own creation. And if the echoes are real, they could rewrite cosmology's biggest questions. The universe's expansion rate, dark energy's mysterious push, even the arrow of time, all might trace back to how the quantum drumhead first stopped ringing and what harmonics were left ringing in the silence. It's a humbling thought that every black hole merger we detect isn't just a death knell for stars, but a message in a bottle from the moment existence decided what it would be. What if everything we experience, the stars, the planets, even the thoughts in your head right now, aren't the products of natural laws, but glitches in an unfathomably advanced quantum simulation? The simulation glitch hypothesis takes the idea that we might live in a computer-generated reality and cranks it to cosmic extremes, suggesting the Big Bang wasn't the birth of a universe. It was the boot-up sequence of a hyper-sophisticated program, one that's been running and occasionally crashing for 13 billion years. Picture this: the earliest moments of our cosmos weren't governed by quantum probabilities, but by the rendering limits of whatever system is hosting us. Just as a video game stutters when too many pixels load at once, the universe's initial singularity might have been a processing overload, a cosmic buffer struggling to handle the sheer complexity of spawning reality. Those infinitesimally hot, dense conditions, not a natural state but the simulation's brute force solution to avoid crashing, like a programmer hitting approximate on a calculation too vast to solve precisely. The cosmic microwave background, that afterglow of creation, could be the equivalent of compression artifacts in a digital image, subtle pixelations where the system cut corners to keep things running smoothly. This taps into philosopher Nick Bostrom's infamous trilemma. Either civilizations always go extinct before mastering simulation technology, they choose not to create ancestor simulations, or we're almost certainly living in one. But the quantum simulation twist adds a darker layer. If our universe is a simulation, its quantum quirks might not be features. They could be bugs. Take entanglement, where particles instantly influence each other across vast distances. In a classical computer, this would break causality, but in a quantum computer, it's just parallel processing. Similarly, the universe's superpositional dawn might reflect a system lazily deferring calculations until someone looked, conserving computational power by only rendering what's observed. Critics argue this is unfalsifiable. How could we ever prove we're in a simulation if the simulators control all the evidence? Yet supporters point to eerie anomalies. Certain cosmic constants are suspiciously fine-tuned for life, like variables tweaked by a coder. The Planck length, the smallest meaningful unit of space, might be the simulation's pixel size. Even quantum indeterminacy could be the program's way of masking unrendered detail, like a video game lowering resolution for distant objects. But here's the real kicker. If this is true, then the Big Bang wasn't the beginning, it was a patch. Maybe our universe is an experimental fork of another, or a recovered save file after a previous iteration crashed. Those gravitational wave echoes, the cold spots in the cosmic microwave background, the way particles sometimes behave differently when measured, they might not be mysteries of physics, but the equivalent of corrupted sectors on a hard drive, hints that somewhere beyond the edges of our reality, a system administrator is watching, debugging, or worse, considering a shutdown. From Schrödinger's cosmos flickering between realities to black holes birthing universes inside their crushing depths, we've journeyed through theories so wild they blur the line between physics and philosophy. The idea that our universe began as a quantum superposition isn't just a tweak to the Big Bang, it's a total rewrite of creation's first draft. Picture a cosmic dice roll where every possible outcome played out at once, and somehow, against incomprehensible odds, this version of reality stuck. Whether it was dark matter nudging probabilities into place, phantom energy freezing the quantum foam into structure, or even neutron stars humming the universe's first resonant frequencies, each theory offers a dizzying glimpse into how fragile our existence might truly be. But here's the kicker: these aren't just thought experiments. Labs are already hunting for proof. Gravitational wave detectors sift spacetime for echoes of that primordial collapse. Particle colliders recreate fractions of a second after the Big Bang, searching for Higgs field hiccups or supersymmetric particles that might explain why matter won out over antimatter. Even the cosmic microwave background, that ancient afterglow, could hide signatures of holographic origins or fractal patterns woven into the fabric of reality. The frontier of quantum cosmology isn't just about untangling the past, it's about realizing how much of that past is still unresolved, still vibrating in the superpositional shadows. So which theory feels closest to the truth? Is our universe a hologram projected from a higher dimension, or one branch of an infinite multiverse? Did consciousness itself stitch reality into being, or are we just lucky survivors of a cosmic lottery? Drop your favorites in the comments. We'll run a poll on the most mind-bending pics. And if you're craving more, hit subscribe. Up next, we're diving into the experiments actually testing these ideas, from quantum gravity probes to simulations hunting for glitches in the matrix. Because the wildest part of this story isn't just how the universe began, it's that we're here at all, piecing together the puzzle.